Hello, good afternoon. My name is Kampianakis Eleftherios. I come from the Technical University of Crete in Greece, and I will present you a wireless sensor network operating with bistatic backscatter principles for measuring environmental humidity. Firstly, we will see the backscatter sensor network principles. How does a point-to-point link operate, and how does a network operate? Then I will show you the development of a backscatter sensor network that measures humidity using bistatic backscatter communication principles. Then I will conclude with some results and acknowledgements. Let's begin with the first. Nowadays, there is an urgent need for ultra-large scale, ultra-low cost, and ultra-low power environmental sensing. For example, in the vineyard shown here on the left, the farmer wants to know exactly the condition of each plant, and the number of plants may come up to thousands or tens of thousands. In order to achieve precision agriculture. Therefore, we need deployments of thousands or more network nodes. The classic wireless sensor network approaches, such as Zigbee radios that use active radio modules, are impractical for such deployments due to cost, power, and complexity constraints. Therefore, we propose a solution that we call bistatic backscatter sensor networks. So let's see the principle behind the bistatic backscatter radio. The RF front end of such a radio includes only a single transistor and an antenna. The transistor switches the termination load of the antenna between two states with a rate, albeit FSW. Then, when a carrier is present on the antenna with the frequency albeit FC, two subcarriers appear on the frequency spectrum, FC with frequencies FC plus minus FSW. This way you can have single transistor microwatt power communication. This technique is applied on the famous RFIDs, is used by the famous RFIDs, but is limited to short communication ranges. In our approach, we are utilizing a so-called bistatic dislocated topology. That is, the reader is detached, is in a different location from the location of a carrier emitter. Therefore, we have achieved greater ranges by introducing dislocated topology, energy-assisted tags, or semi-passive tags, and low bitrate since we are having environmental sensing applications. Using these techniques, we managed to achieve backscatter communication ranges for a point-to-point link of over 100 meters. So we've seen how the point-to-point link operates. Now let's see how to build a network. If we utilize multiple low-cost emitters and one receiver acting as an information sink and spread around the emitters a couple of hundred tags, then we can have networks of a scale of more than 1,000 tags. So you see that we have low cost and low power nodes and a low cost in general scheme to solve the problem. So let's see a proof of concept implementation that we have developed in the Technical University of Crete. We developed the sensor node shown here, the tag node shown here, with a capacitive humidity sensor made from Honeywell, the HCH1000. It comprises of a timer circuit connected, a timer IC connected to an RC network. The RC network also includes the capacitive humidity sensor. Therefore, when the timer produces voltage pulses, these pulses, the frequency of those pulses, are actually controlled by, the frequency of those pulses is controlled by the humidity sensor attached to the RC network. These pulses are then driven to the RF front end and the transistor, and in a way that frequency modulation of the humidity can be achieved. So, when you have multiple tags, all you need for a network is a medium access scheme. We achieve medium access by utilizing different RI and CI on the RC network of each tag in a way that each sensor is allocated a different frequency band. So sensor 1 has a different RI and CI from sensor 2, and in between we allocate guard bands, frequency guard bands, in order to avoid collisions. This way we achieve frequency division multiple access scheme, a simple frequency division multiple access scheme, which you can see in operation in the spectrum here from a spectrum analyzer. You will see that a frequency shift is imminent between a 20% RH and a 40% RH, specifically a 5 kHz shift in frequency. To continue, we deployed multiple of those tags with the FDMA scheme, with the frequency division multiple access scheme that you've seen before, in indoors and outdoor environments. We utilized a software-defined radio platform for our receiver, which is the USRP platform, a flexible platform for reception of our signals. And we deployed the network so much in an outdoor and an indoor setup. Here you can see the measurements of the frequency of 10 tags deployed outdoors for a total of 8 hours. You can see that almost all tags follow the same pattern because they are placed in the same environmental conditions in this outdoor deployment. You can also see the lost measurements over here, which are induced due to the probability of error of a wireless channel. Now let's see some results. The sensor totally consumes 200 microamperes at 2 volts, which means that a 1.2 years lifetime is achievable with a 2000 milliamperes battery. And important to note is that the tag is always on. We do not utilize any complex duty cycling schemes that require cooperation between the receiver and the tags, etc. That is utilized by almost all wireless sensor network nodes in order to achieve long battery lifetime. We calibrated multiple of those tags using an environmental chamber, and since we're having a multiple access scheme, we can calibrate a lot of tags at once. We've taken a number of frequency measurements along with the humidity measurements from an industrial reference precision humidity sensor, and applied polynomial fitting to our measurements. Therefore, we resulted in an RMS error of 0.9 percentage of RH. The measurement range that we achieved was from 20 to 90% RH, as well as the maximum communication range of 120 meters of a point-to-point link. Now let's see a bistatic backscatter demonstration, which we've done in order to characterize the range of a point-to-point link. Here you see on the left, from the left to right, the carrier emitter, the sensor tag inside the cooler box to maintain around the same environmental conditions, and the USRP receiver. Here's the sensor inside the cooler box with the humidity sensor attached. Now we measure on the receiver, which is attached to a computer, a percentage of relative humidity of around 23%. You see that it's the same setup, the USRP receiver, the tag inside the cooler box, And once we move the equipment really fast to 50 meters, we should observe around the same humidity value. I say again that it was only to characterize the range, not the accuracy of the system. So, if we check the humidity again, it should be the same value, and it actually is 23% with a slight increase due to the heat. Okay. So to conclude, we've seen a demonstration of a first-of-a-kind bistatic backscatter radio sensor network, which utilizes a low-complexity network scheme. And I say that this is important because one of the main constraints for scalability in the classic wireless sensor network approaches is the complexity. If we manage to lower down the complexity of the system, we can manage to upgrade the scalability. We also seen a demonstration setup that was developed and deployed indoors and outdoors that monitors percentage of array with a relatively good accuracy, and that our next goal is a proof of concept of an ultra large scale network of more than 1,000 tags. Here you can see some references of our work and more information about the bistatic backscatter architecture. Thank you very much. Also, this was a project in the context of the Blaze project. You can see also a website here for more information and some contact information. Thank you.